These are the topics that we're going to be going over: elements and their symbols, periodic table, atomic structure, isotopes, and electron arrangement. Now, elements and compounds are part of pure substances, and today we're just going to be focusing on elements, and then the following chapters we'll look at compounds. So for elements, we always have one type of atom present. An example here is copper, and we see a copper atom. But for compounds, there's always more than one type of atom present. Now we have here the example is water, and we can see the hydrogen atoms and the oxygen atoms in our samples. So how many symbols of the elements do you know? So here are a bunch of elements, and I've covered over their symbols. I'd like you to take a piece of paper and write down what you think the symbols might be. So you want to pause this, pause the slide, and then come back and take a look at the answers. Okay, and here are the answers here. You notice that all the symbols begin with a capital letter, and you see the capital letter here. Some have one letter, some have two. If they have two letters, the second letter is always small, and it's supposed to be an identifying letter to help you remember the name. And you notice that we have a whole bunch with C's. God, there's a lot of them here. So only one of them can just have the C for the symbol, and that's carbon. But we have like Ca for calcium, Cd for cadmium, so D identifies that. Chlorine is Cl, not Ch, some people believe that. Chromium is Cr, cobalt Co, and copper is Cu. Now, the reason it's Cu is because it's from the Latin name for copper. So elements that were known for hundreds of years have Latin names, and that's where the symbols came from. Now, here's what a lot of people got wrong. Fluorine is capital F, not Fl. All right, here's another group you should all know. So again, pause the slide, write down what you think their symbols are, and then come back and see how well you did. And you can notice that we have 4 of them here that will have symbols that will be based on these Latin names. Okay, and so here we go with the answers. So we have, notice gold, Au, iron, ferrum, plumbum is lead. Now a person that works with lead is called a plumber. Mercury, Hg, that's one a lot of people get confused with. Now here are some more. So you want to pause the slide, and then you want to check your answers. Okay, so here are the answers again. All right, how well did you do? You want to pay special attention to those that, again, have a different name from the symbol, like potassium and silver and sodium and tin. We have stannum here. All right, elements, pure substances that cannot be separated into simpler substances by ordinary chemical processes. Now, we can take elements apart, but when we take them apart into the separate atoms, the particles that we come up with are common to all atoms. So we're not saying you can't break those atoms apart, but once you do, you don't get smaller basic substances like these. All right. Excuse me. So here are some names and symbols of common elements as you saw earlier, and you have some of the examples up here. So we have aluminum, like you see aluminum foil would be the same as this. Carbon, this would be the same carbon as you get on a piece of toast if you cook it too much. We have gold, although it looks a little coppery here. That's gold. Silver, looks like it's reacted a bit. That's what looks kind of dark here. And the last one is sulfur. You notice there are 2 U's in sulfur. It doesn't end with an ER. And sulfur is a yellow powder. So those symbols you should all know and be very familiar with them. Now, one of the people get confused with many times is silicon. If you go back here, you see silicon is Si. See it right over here. And that's the element silicon. Now, silicon is a compound, and this is what a molecule of it looks like. And you see it has 2 silicon atoms in it, but it also has 3 oxygen atoms, and it has these 3 groups, these 4 groups actually. These are called methyl groups, and you can see how they're arranged in them. And we'll be looking at molecules like this at the end of the course. All right, now we're on to the periodic table, and it's really the periodic table of elements. And so the first thing we have is separating the periodic table into the 3 basic types of elements. So what we have in blue are metals, and you can see that most of the elements then by far are metals. And then in green we have what we call the metalloids. They kind of border this black staircase. And then to the right of them we have the nonmetals. So let's check out some of the properties of these. So metals are shiny and ductile. Ductile means you can make wires out of it. They're also malleable, which means you can form them into different shapes. They're good conductors of heat and electricity. Now, nonmetals, on the other hand, are the opposite. Dull, brittle, poor conductors. If anything, they're good insulators. And the metalloids are better conductors than nonmetals, but not as good as metals. And the metalloids are used as semiconductors and insulators. Now, one good semiconductor, of course, is silicon, which is used in computer chips. So here's our basic periodic table, and this will be like the one in your book. You probably have one in the front of the book, right on the front cover. If you turn it open. All right, so the first thing we want to do is notice we have a lot of symbols in here and numbers, and they're also giving you the names of some of these groups. So the groups are the vertical columns, and if you count them all, it goes from 1, you see 12, all the way up to 18 different groups. And then we also further subdivide these groups as A and B groups. Now the A groups are what we call our representative elements. So we have 1A, 2A, and you notice it's 3A all the way to 8A. Now, a lot of times these B groups are not representative, so we're not going to talk about them too much, especially in terms of atomic structure. Now, the horizontal groups here are called periods or rows, and so if you count them, we have 7 rows. Now, these two down here are actually pulled right out of the middle of row 6 and 7. If they left them in there, it would make the course of periodic table twice as wide. There are other reasons in terms of atomic structure that we may see a little bit later as well. So again, here is the periodic table, and now we're going to look at the families. So we have the alkaline metals over here. They're the most chemically active metals. We have the alkaline earth metals next to them. You see some common metals like calcium, magnesium in here. Then the metals in the middle are the transition elements, transition metals, and those would contain the common metals like gold and silver and copper and lead. Now over here, we have a group of elements made up of some metals, some nonmetals, and some metalloids, and their families don't have any names. Now we go to the last two in the end. Group 7A, called the halogens. They're the most chemically active of the nonmetals, and on the far right we have the noble gases, and they don't react with anything, which is their real claim to fame. So you should know where these groups are located. So there's really 5 you have to know. Alkaline metals, alkaline earth elements, transition metals, halogens, and noble gases. Now let's take a look at the alkaline metals in particular. These metals are so reactive that if you put them into water, it will explode in the water. Now what they have here is a liquid, but it's not water, it will be oil. So these guys are very, very chemically active. If you want to see these metals being added to water, you can go online to the video periodic table out of the University of Nottingham in England, and you can actually watch little videos of these people performing all sorts of experiments with the elements. They're really cool. The halogens on the other end of the table, sorry about that, I think that's from my email program. It's actually the sound of the sea, so you guys may appreciate it. So we have the halogens here, the most chemically active nonmetals. We have fluorine, chlorine, bromine, and iodine. And you see that chlorine is this yellow greenish gas that you smell when you smell bleach. Bromine is actually a liquid at room temperature, but it easily vaporizes. That's why we see the gas up in here. And iodine itself is a solid at room temperature, but it easily vaporizes as well. And all of these now are toxic to us, so we have to be careful of them, and they're very chemically active. So here's a learning check for you. So look, just using a periodic table, see if you can identify the various elements you're asked about. And then come on back and we'll see the answers. So you might want to pause the video. Okay, for A, group 7A, period 4, that would be bromine. So you want to view the periodic table like it's a map. So just like you have streets and avenues, on the periodic table we have groups and periods. For letter B, group 2A, period 3, that would be magnesium. And for letter C, group 5A, period 2, that would be nitrogen. Good. Now we're going to start up on the atomic theories and how they changed over time. The first fellow that gets any credit for coming up with a theory that involves atoms was a Greek philosopher named Democritus, around 400 BC. Now, at the time, people either believed that you could break matter down into smaller and smaller pieces, and it would never end. There was no end to that. You could do it forever. And then there was another small group of people that thought that you'd break matter down into smaller and smaller pieces, but at some point you'd wind up with the basic particles of matter. And Democritus called those atoms. And atom is from the Greek word atomos, which means eternal and indivisible. Now, Democritus pictured atoms as having various geometric shapes like you can see here. And atoms would stick together to give us the types of matter that we see around us. And the only thing he could come up with that would give them a reason to stick together is they have these little hooks on them. So because of those little hooks, they could stick together and give us everything we could see. Now, his idea didn't go over too well with the religious people of the day, because he also said your spirit is made of soul atoms. And because of that, they ran him out of town on a rail. Of course, they didn't have rails back then, but threw him out of town. Okay, we jump all the way up to about 1780 when Antoine Lavoisier was also called the father of modern chemistry. Lavoisier was a great experimenter, and he found that when he did reactions, that the mass before and after the reaction stayed the same. Now, he didn't know why that would happen, because at that time people thought that the mass always got smaller. Like when you burn wood, the wood weighs a lot more than the ashes do that you get after you burn the wood. So he thought this was kind of strange. So he makes this observation. Another fellow, Joseph Proust in France, came up with the observation about decomposing some compounds. Now, he used copper carbonate, and when he decomposed varying masses of it, he always got the same ratio by mass of the elements copper and carbon and oxygen present. Always the same ratios. He couldn't explain that either, but he thought that was interesting to note. It took John Dalton in 1800 to come up with a theory that would try to explain the observations of Proust and Lavoisier. So Dalton thought if matter were made up of atoms, that could explain both observations. Now, he didn't use the idea of Democritus about the atoms, but he thought that atoms might be small, round, and hard. Each element would have its own atom, and these atoms could stick together to form compounds. Now, the basic difference between atoms of elements he thought would be mass. Some would be heavier than others. So this is Dalton's billiard ball theory. Now, if you take a look at it, we have some atoms of element X. We're going to take 16 of them. And he said if you take 16 of element X, they might combine with 8 atoms of element Y to give us a compound. If you look at it, what would the formula be? Well, it would be XY2. 2Y. I'm sorry, just the opposite. X2Y. And here, if you count up all the atoms, there's 24 atoms altogether, then we're ending with 24 atoms. There are 8 of these groups, and each group has 3 atoms in it. So this would account for or explain Lavoisier's observation as well as that of Proust. About 100 years later, the electron was discovered by J.J. Thomson. Now, he knew that matter could produce these electrons, and if matter is made of atoms, then the electrons had to come from atoms. But if our atoms were round and hard and dense like Dalton thought, then the electrons would never be able to escape them. So he thought atoms couldn't be round and hard and dense like that. So his model of the atom is called the raisin pudding model. And in his model, an atom is more of a fluid, like a pudding, and it has these negative electrons embedded within the atom. And I notice he's not talking about any other particles in there, just the electrons. And to balance off the charge of the electrons, he said you must have a positive charge in here somehow spread around. A fellow that worked for him at the time, another very famous scientist, was a fellow named Ernest Rutherford. Now, Rutherford had discovered the 3 basic types of radiation, alpha particles, beta particles, and gamma rays. And he'd been doing a lot of experiments with radioactive substances that could produce these radioactive particles. So he thought that he would test Thomson's idea about atoms. And so he took a piece of gold foil, as we're going to see here. He took a piece of gold foil and he aimed a beam of alpha particles at it. Now, he expected all of the particles to pass right through the gold foil because, atoms were supposed to be made of a pudding. And what he found with these results, that some of the particles, some of his alpha particles were scattered to the side. Every once in a while, one came almost directly back at him. Now, he said it would be like if he fired a gun at a piece of tissue paper and the bullet bounced off the tissue paper and came back and hit him. This is how he explained what must be happening. Again, excuse me on that. So here come the alpha particles. Most of them would pass right through the atoms. But every once in a while, one of them must come close to the center of the atom and then get deflected to the side. Now, alpha particles have a positive charge, so he said, whatever that center is, it must have a positive charge as well if it can repel these. And every once in a while, a particle comes directly back like that atom. So he said this little center must be also very massive. It could knock a particle back like that. So he concluded that an atom is mostly empty space that contained a nucleus that was small, dense, and positively charged. Now you notice he's not saying anything about electrons. He said, I'm going to let somebody else figure that one out. So our basic atom today, we have a nucleus in the center containing protons and neutrons, and we have electrons around it somehow. The neutron was the last subatomic particle to be discovered. It wasn't discovered until around 1933. So let's take a look at some of the properties of these particles. So a proton and a neutron have almost the same mass, so they created a unit called an atomic mass unit. There's not anything you could weigh on a scale, but you see what it means. If we just assign a mass of 1 to a proton, the neutron has about the same mass. And because electrons are so small, they have about a mass of 0 AMUs. And the charges, a proton plus 1, electron has a charge of minus 1. So electrons and protons can neutralize each other, and a neutron has no charge at all. Now inside an atom, two things you have to know. Atomic mass is going to be the sum of the protons and the neutrons, and atomic number is going to be the number of protons and it's the number of electrons. It's going to be both.